What's up? I'm Vin, and today I want to explore the mean value theorem. And the mean value theorem states if f of x is continuous on the closed interval ab and differentiable on the open interval ab, there must be a value c where c is between a and b such that f prime of c equals f of b minus f of a over b minus a. Now, this is a lot to unpack, but a nice way to understand this theorem is to transfer it over to the graph. So the first thing I want to explore is the right side here. F of b minus f of a over b minus a represents the average rate of change, which I'll abbreviate with AROC. And when I think of it on a graph, I plot this point a f of a, and I plot the point b f of b, and I connect these points with the straight line. And the slope of this line that I'm drawing in right now represents the average rate of change of f of x from a to b. So now what the theorem is actually saying here is that as long as our function is continuous on the closed interval and differentiable on the open interval, which just means that this red curve is not only connected, but it's smooth and it has no sharp turns, that as long as those conditions are met, then at some point you're going to have a value c between a and b where the slope of the tangent line, the instantaneous rate of change, is going to equal the average rate of change. So now let's look at a copy of the blue line I drew in a moment ago. This represents our tangent line, so I have to place this strategically. It's going to go at about this location here. And now the slope of this tangent line represents our instantaneous rate of change. That's f prime of c. So the value c is the value of x that is between a and b, where the slope of the tangent line is equal to the slope of the secant line. And remember from geometry, slopes are equal when you have parallel lines. So it's no coincidence here that the blue line and the purple line are in fact parallel. So that's what I'm imagining here, that when I have my continuous and differentiable function, that at some point between a and b, the slope of the tangent line is going to gradually match up with the slope of the secant line. So you can see right now, if I look at this tangent line, it doesn't match the slope that we have in blue, but as we get closer and closer to point C, we could see that exactly when we get to point C here, that the slope of this tangent line is matching the slope of this secant line. So now let's look at a few questions that cover the many ways the mean value theorem could show up in calculus. So we have a graph of f of x, and we want to know for how many points is the instantaneous rate of change equal to the average rate of change on the closed interval 1, 4. So the first thing I would do here is just mark off this closed interval. We're going from x equals 1 to x equals 4. And I'm going to look at the points on the function here. The point here, 1, 1. And we're looking at the other point over here at 4, negative 1. So these are the important points to highlight here. And I'm going to connect those points with a straight line. And this line is our secant line. And the slope of this secant line is our average rate of change. Okay, so let me just line this up as nicely as possible. So the slope of this line in black is our average rate of change. So what we're looking for is for how many points is the instantaneous rate of change equal to the slope of this black line. And remember, the instantaneous rate of change is the slope of the tangent line. Okay, so the slope of the tangent line is the instantaneous rate of change. So this is important to know. So now I transfer this over to the graph here. And you could see at, let's say this point over here at the peak, we have a slope of 0 because this is a turning point. So then after the turning point here, as we start to drop, that's when our slope goes negative and will match this slope of the black line the first time. So over here, notice this is where the slope starts to become negative. And at about this location here is the first time that the slope of the tangent line matches the slope of the secant line. So then we start to drop here. Just imagine you're on a roller coaster. And at about this location here is when we're dropping really fast. But then as we start to turn here, the slope becomes less steep and starts to flatten out when it gets here. So at about this location here is the second time that the slope of the tangent line is going to match the slope of the secant line. So far we have 2. So this one is out. And then we start to rise and we have a positive slope, which is not going to match. But then we get to the peak, we have a slope of 0, and then we start to drop again. So this is the third time that the slope of the tangent line matches the slope of the secant line. So we have at least 3, but then notice here we turn once more to a slope of 0 when we end at 4. So at about this location here is the 4th time that the slope of the tangent line matches the slope of the secant line. Let me just draw that a little bit neater. So this, we have to just draw them parallel like this. So this is the 4th time that it happens. So choice C is out. Choice D is our solution. Question 2, we have f of x equals x times natural log x, and we're on the closed interval 1, 3. And we want to know, does f of x satisfy the mean value theorem on this interval? And if so, find the value c between 1 and 3 that satisfies the conclusion of MVT. So for this question here, in order for us to be able to use the mean value theorem, our function f of x has to be continuous on the closed interval 1, 3 and differentiable on the open interval 1, 3. And f of x satisfies both of those. Now, we don't have to write the most rigorous explanation as to why f of x is continuous and differentiable, but my quick reasoning as to why this function is continuous and differentiable is I think of both functions separately, the functions that build f of x. If we think about, let's say, y equals x and y equals natural log x, if we look at both of those functions side by side, y equals x is a continuous and differentiable function. So this is the function y equals x. And if we look at y equals natural log x, the domain for natural log x is greater than 0. Okay, so that would be our domain of this function here, whereas our domain for y equals x is all real numbers. So the fact that they gave us the closed interval 1, 3 puts us on a part of the graph where natural log is continuous and differentiable. So we're not going to run into any trouble here. So then the next thing that we have to think about is the formula for the mean value theorem, which, remember, at the end we said f prime of c equals f of b minus f of a over b minus a. So for a question like this is just a very technical question where you're just applying the formula after we verify that this function satisfies the hypothesis or the conditions to use mean value theorem. So now we'll go ahead and apply the formula. So f prime of c, to find f prime, we're going to have to take the derivative of f of x. So we're going to have to use the product rule here. So we have f prime of x is equal to, and I'm taking the derivative of x is 1 times natural log x, and then I'm adding, we have x times the derivative of natural log x is 1 over x. So that brings us to this step. We have f prime of x is equal to, and we're going to have natural log x plus 1. And now the next thing we could find is the average rate of change of f of x from 1 to 3. So I'm going to say here the average rate of change we're going to find by doing f of 3 minus f of 1 over 3 minus 1. So now we just plug into the original function here to find these values. So f of 3 is 3 natural log 3. And we're subtracting 1 times natural log 1 and dividing by 3 minus 1, which is 2. Now, a nice thing to know here is that natural log of 1 is equal to 0. You could just see that over here on the graph like this. So this piece just cancels out, and that tells us that our average rate of change here, if we simplify it, the average rate of change is equal to, we have 3 ln 3 over 2. So now that we have the instantaneous rate of change and the average rate of change, we could solve for the value c. So we're setting f prime of c. So f prime of c, we could just say, is natural log of c plus 1. We're setting this equal to 3 ln 3 over 2. And now we just have to do the algebra. So we're going to subtract 1 on both sides like this. The 1 minus 1 is going to cancel. And we're going to have natural log of c is equal to, we have 3 ln 3 over 2 and then minus 1. And now to get c by itself, there's a natural log attached. And the opposite of natural log is the function e. So what we're going to do from this step here is we're going to exponentiate both sides. We'll make both sides powers of e like this. So then this tells us the value of c. The value of c is equal to, we're going to have e to the 3 ln 3 over 2 and then minus 1. This is all an exponent of e. And this is our value of c. So now let's check to see that our answer is reasonable. So we have e to the power, and that fraction, I'm going to write alpha y equals enter to pull up a blank fraction. And we have 3 natural log 3 up top. And then on bottom here, we have 2, and then I'll exit the fraction here and tack on the minus 1. So this is our value of c, and notice that it falls between 1 and 3 as the mean value theorem guaranteed. So this is a really good sign. And now I'm going to store this as the letter a, just so I don't have to keep writing that decimal over and over. So now I'm going to press math 8, and we're going to take the derivative with respect to x of x natural log x, and I want to check this out here at the point we just found. So I could just go ahead and type in alpha math here to put in the letter a, and that'll type in the value that we just stored it as like this. Or another way to do this is I could just scroll up to the number like this and press enter, and it'll input the number here. So this is going to take the instantaneous rate of change at this value. But what I could also verify here is the average rate of change we just found a moment ago. So if I go ahead and press alpha y equals enter, we said it was 3 natural log 3 and then minus 1 natural log 1. We'll pretend we don't know that piece is 0. And then we're dividing by 3 minus 1. And if we did this correct here, the numbers should in fact match, and they do. Okay, now you might say, oh wait, this is off by a little bit, but the calculators are only so perfect. When you get values like this, you should feel very confident in your answer, e to the power 3 ln 3 over 2 minus 1. Question 3, we have assume f of x is a differentiable function with select values in the table below. And here's our table of values. And we have to explain why there must be a value c, where c is between 0 and 8, such that f prime of c is equal to 1. So for a question like this, if we're going to explain with the mean value theorem, we have to first make sure that we can use the mean value theorem. And I know we could use the mean value theorem here because they told us f of x is differentiable. And once you know that f of x is differentiable, differentiability implies continuity. So now that we established that f of x is differentiable and continuous, the mean value theorem does apply. So now let's think about how do we apply the mean value theorem here. So think about the conclusion of the mean value theorem. The conclusion says that the instantaneous rate of change is going to be equal to the average rate of change at some point c, where c is between a and b. So for the next part of this question here, it becomes a scavenger hunt. You're looking for 2 points in the table that when you find the slope between those 2 points, the slope is equal to 1, because that's the target value for our instantaneous rate of change. So if you look at the table here, you could see the first and the last point. If you find the slope between those 2 points, so we'll think about that over here, the slope between those 2 points, if we do the difference of the y values or the difference of the f of x values, we have 10 minus 2 divided by the difference of the x values is 8 minus 0, and that gives us 8 divided by 8, which simplifies to 1, which matches the instantaneous rate of change that we want. So now we're ready to apply the mean value theorem. We could say by the mean value theorem, and we'll abbreviate with MVT, there must be a value c. That we could abbreviate. The there must be a value, we could abbreviate with this backwards capital E. I promise the backwards capital E means there exists. So I could say there exists a value c, and c is between 0 and 8. Such that, and for this part, we have to be very, very careful, okay? Don't just say f prime of c equals 1, because then we're assuming the conclusion. We have to show that the conclusion is true. So we're going to say here that f prime of c is equal to the average rate of change, and we chose the endpoints here from 0 to 8. So now we could use the average rate of change formula, the f of 8 minus f of 0 over 8 minus 0, okay? So we're applying the average rate of change formula to the endpoints, and then show what it simplifies to. It simplifies to 10 minus 2 divided by 8 minus 0, and 8 divided by 8 equals 1, which is exactly what we were trying to show at the end here. So this wraps up our explanation. Question 4, which of the following satisfy the hypothesis of the mean value theorem on the closed interval 0, 3? So for a question like this, I'm thinking about which of these functions are both continuous on the closed interval 0, 3. So we need f to be continuous. So f is continuous, and I'll abbreviate, on 0, 3, and we need f of x to be differentiable. So f is also differentiable on the open interval 0, 3. Okay, so these are the two conditions that have to be met in order for the function to satisfy the hypothesis of MVT. So let's start with Roman numeral 1. So we're going to look over here at f of x. So we have f of x is equal to x to the 2/3. Now I could write this another way here. This I could also write as the cube root of x squared. So now think about it. Is there any number that you can't square and then take the cube root of? There's no restrictions on that. So the domain here is all real numbers. So f of x is continuous for all real numbers. So far so good for Roman numeral 1. But now I'm going to look at the derivative here, f prime of x. If we take the derivative of this function, we're going to have 2/3 x, and then we subtract 1 here. We have 2/3 minus 1 is negative 1/3. And if I rewrite this another way, this is 2 over 3, and I send this x to the negative third down as x to the positive third. And this I could even express one more way. Let me just write that a little bit neater. So we have x to the power 1 over 3. So we have to the 1/3. This I could write as 2 over 3 times the cube root of x. And the value of x that would ruin this would be x equals 0. Okay, so I would say here that f prime of 0 is undefined, which then tells us that f is not differentiable. Okay, f is not differentiable at x equals 0. But this is not a problem because remember, that's the only value of x that ruins our derivative. This is not a problem because we only need to be differentiable on the open interval 0, 3. So the fact that we're not differentiable at 0 is not a problem. So Roman numeral 1 is good. If you were to actually look at a picture of this function, this I like to call the bird function, because if you're not a great artist like me and you draw birds in the distance of your drawings, this is probably what your birds look like. So at that sharp turn here is the only spot where f of x is not differentiable. So 1 is allowed here. So 1 keeps all the answer choices alive here. So now we move on to Roman numeral 2. And for Roman numeral 2, what we have is we have the cube root. So we have f of x is equal to the cube root of x minus 2. So just looking at this function here, I look at this and say, all right, I could take the cube root of anything. So the domain, all real numbers, but now call this x minus 2 to the 1/3. Now I'm going to take the derivative. F prime of x is equal to 1/3 x minus 2. And when we subtract 1, we get negative 2/3. Okay, I technically would apply the chain rule here, but the derivative of the inside is 1, so nothing exciting is going to happen out of that. So now I'm going to rewrite this as 1 over 3 times the cube root of x minus 2 squared. But now you see the problem with this one is that f prime of 2 gives us a denominator of 0, so f prime of 2 is now undefined, which means that f is not differentiable. So f is not differentiable at x equals 2. This is a big problem because notice how 2 is between 0 and 3. So that would ruin that second condition. This function f of x from Roman numeral 2 is not differentiable on the open interval 0, 3. So this one is out. Okay, so choice B is out and choice D is out. So now it's just a matter of determining if Roman numeral 3, this f of x, is continuous on the closed interval and differentiable on the open interval. So now let's investigate Roman numeral 3. So for this one, I want to look at a different function first. I'm going to call it g of x is just x squared minus x. So we have this quadratic function, and I'm going to factor out an x, and we have x times x minus 1. So if I look at a graph of this function, we have a root at 0, and we have a root at x equals 1. So this is a smiling parabola if I were to draw it out, and this is what the function of g of x looks like. So f of x, if you notice, f of x is the absolute value of x squared minus x. So what that does is it takes the original graph that we started with, and instead of it going under the x-axis between the roots, it's going to bounce up like this. So it's going to go like this at 0, it's going to bounce up, it's going to come back down, and it's going to go up again like this. So notice that we have two sharp turns here. So for this function in pink here, I'm going to say f of x is not differentiable. So f of x is not differentiable at two values of x, at x equals 0 and x equals 1. So notice 1 falls on that open interval between 0 and 3. So that will eliminate Roman numeral 3 because once again, the fact that f is not differentiable at 1 is a problem when we look at this graph here of the absolute value of the quadratic. So that tells us that only Roman numeral 1 satisfies the hypothesis. So choice A is our answer. So for our last question, question 5, we have f of x is equal to tangent inverse x plus e to the x, and we're on the closed interval 0, 1. Does f of x satisfy MVT on this interval? And if so, find the value c between 0 and 1 that satisfies the conclusion of MVT. So for a question like this, we have to use the calculator. So I want to first think, does this function satisfy MVT? And it does, because I'm thinking about tangent inverse x. Tangent inverse x, if we look at a graph of it, looks something like this. Okay, so it's going to look something like this. It has horizontal asymptotes at pi over 2 and negative pi over 2. That part is not important. What is important is that this function here is continuous from 0 to 1 on the closed interval, and it's differentiable on the open interval from 0 to 1. So we're not going to have any problems there. And if I think about e to the x is a nice function. It's an exponential function. It is continuous and differentiable everywhere. So the combination of these two functions is not going to give us any problems. So now let's think about what we need to find our value c here. We need to find a value c such that f prime of c is equal to the average rate of change from 0 to 1. So that's going to be f of 1 minus f of 0 over 1 minus 0. So we'll use the calculator to find our value of c here. We're going to go over to y equals, and we're going to type in tangent inverse is second tangent, and we write in tangent inverse of x. There's our variable button. And then we're going to write after the parenthesis here, we have plus e to the x is second natural log. That pulls up e to the x, and we just input the x. So there's our function f of x, and once we have this, we could find the average rate of change on the main screen. So I'm going to press alpha y equals enter, and now a nice shortcut to find f of 1 and f of 0 is I could press alpha trace if I have the TI-84 plus CE. If you have an older calculator, this might not show up, so I'll show a second way right after this. But if you press alpha trace, it's going to pull up the y1 button, and we wrote f of x in the y1 spot. So if I want f of 1, I put y1, I put a parenthesis 1, and then I close the parenthesis around the 1. And then I write minus, and once again, if you have an older calculator, you could press vars, go to the right over to the y vars, and then function. You'll also find the y1 saved here. The first button sequence is just a little bit faster. So now we have f of 0, so I put parentheses 0 and then close the parentheses here. And then on the denominator, we're going to have 1 minus 0. So we have f of 1 minus f of 0 over 1 minus 0. We press enter, and this is our average rate of change of f of x from 0 to 1. So now I'm going to store this as the letter a, and we'll just say a is for average. So now every time I write a, that number is going to show up. So now I could go over to the y equals, and I want to find out when is the instantaneous rate of change equal to the average rate of change, which we just found is equal to a. So the instantaneous rate of change, I could take the derivative of the top line, but let's say it's something really, really complicated, and I just want to use technology. I press math 8, and that's going to say derivative with respect to, we're taking the derivative with respect to x of the function y1. So I could go to vars, go to the right, go to function, y1, and then this is going to tell the calculator to take the derivative of the equation above it, but we just have to write x equals x here because it's going to take the derivative in terms of x for any value of x. So now I'm going to look at a graph of this, but before I do, I'm just going to go ahead and turn off this equal sign here and press enter. Because if I don't turn this off, I'm going to press zoom 6 so that the graph shows up normal here. Notice that I get a bunch of graphs here, and it could be a little bit confusing in terms of which one I'm looking for the intersection point. So I go over to the original function f of x and I press enter on the equal sign, because we're only interested in when is the derivative f prime equal to the average rate of change. So now I press graph, and notice I have just one intersection point over here between the red graph and the black line, which represents the average rate of change. And notice that the intersection happens between 0 and 1, which is what we want for this question. So now let's say that's a little bit tricky to see. Notice that it's happening between 0 and 1 on the x-axis and about 0 and 5 on the y-axis. So I could go over to the window, I could change my x minimum to 0, my x maximum to 1, and I'll change my y minimum to 0 and my y max to 5. So I like to do this because it makes the picture much bigger and it's easier to see where the intersection point is. So now I press second trace number 5, and now I can look for the intersection point. I go a little bit before, I press enter a little bit after, and then I press enter a third time. And this is the value for C that we need. So this equation is true when C is equal to, and we'll round to 3 decimal places. Notice that in the thousandths place we have a 2, to the right is a 4, so we're going to round this down to 0.552. And now the last thing we'll do is check our answer. Now we already said that our value of C fell between 0 and 1, so that was a good sign, but I'm going to press second mode and go back to the main screen. And I'm going to press second and this minus sign here to pull up the answer. And that's the value of C that we just found. And what we could do is we could plug this value of C into the derivative and see if it matches the average rate of change. So remember, our derivative was in the y2 spot. So I could press alpha trace and pull up y2 like this. And I'm going to go ahead and plug in this value. And a fast way to do it is I just go up to it and I press enter. And then I close the parentheses. And notice that we get an exact match for our average rate of change.